Welcome to the natural exponential function. In this video, we will delve into both the derivative and integral rules for e to the x. Go ahead and begin with our quick warm-up. Hit play when you're done. Here are the solutions to these first four. In reality, this should have only taken you about 10 seconds or so. If it did take you longer, if you did not know the answers to these, we need to do some review. So if you were fine on this, go ahead and skip to the next chapter. But if you were not, let's take a look at number 1. The natural log of e. Well, overall, what does this mean? This means that the base of this natural log function is always e, and so essentially what we're asked is that base e to the what, this is our answer here, e to the what, will give us the output of e. That is how logs work. Well, e to the first gives us e, and that is why the natural log of e is 1. Logs and natural logs are just fancy ways to represent exponents. So this is saying what's the exponent required to get from our base of e up to e? Just 1. So it is imperative that you know that the natural log of e is 1. By that same explanation here, this is asking us e to the what gives us 1. Well, e is just a number. After all, it's 2.718, ... because it is irrational. E to the 0 will give us 1 because any number to the 0 power does, in fact, give us 1. So this is the other one that we should have memorized. And number 3 was a little bit tricky, but it uses the properties of exponents, or it doesn't necessarily even have to. There's kind of two ways to go about this one. We can think e to the what will give us e cubed. Clearly, we see that that what has to be 3. The other way that you can look at this is using the properties of logs. We could have brought that 3 out front, so it's 3 ln e equals what, right? We didn't know the answer was 3 yet. Well, the natural log of e is 1, so this is 3 times 1 is in fact our answer, so it is 3. Then number 4, this is just good to keep in mind that e is, yes, represented by a letter, and in math, a lot of times we think of that being a variable. However, variables are usually at the end of the alphabet. Again, not always, x, y, and z. But e is not a variable. It is a constant. It is approximately 2.718, and so that's always good to keep in mind when dealing with this transcendental and irrational number. We previously learned about the natural log function and inverse functions. Well, the inverse function of the natural log function is e to the x, otherwise known as the natural exponential function. Exponential functions are just a number raised to the x, and in this case, well, a positive number raised to the x, and in this case, the natural exponential function happens to just be the exponential function where the base is e. So the natural log function and the natural exponential function are in fact inverses of one another. This inverse relationship gives us two important ideas. One is that the natural log of e to the x is x. Now we already know that by using the properties of logs, we could bring that x out front. X times the natural log of e. Hey, the natural log of e is just 1, so we end up getting x. This one's a little more complex, however, it still works. And this idea comes to us using the inverse relationship. We're going to use these two ideas to solve problems involving natural logs and e. Here we have 4 problems involving e and natural log. We are going to keep these two ideas in mind here while solving them. We're also going to keep in mind that the natural log and e can kind of cancel each other out in a way because the natural log of e is just 1. And so we're also going to keep in mind that property that we can bring when we take the natural log of something to a power, we can bring that power out front. So in number 1, we have e to the 4 times x equals 20. While we could make a good guess about what this is, maybe it's approximately 1 point something, because e is between 2 and 3, we will not know the exact answer unless we take the natural log of both sides. Now, why do we take the natural log of both sides? Well, for starters, we have that property that says we can bring this exponent out front. So this is really 4x times the natural log of e equals the natural log of 20. What is the natural log of 20? I'm not sure, but our calculator can give us an exact answer. The reason that we do this is because the natural log of e is just 1. So we have, in fact, 4x equals ln of 20. If you did not have a calculator, your answer would simply be that x equals the natural log of 20 and then divided by 4. It's not the natural log of 5, it's not 20 divided by 4, it's the natural log of 20, which is its own number, then divided by 4. In our calculator, we should get 0.748 approximately. I was a little off in the beginning when I said this might be between 1 and 2. E to the 4 times 0.748 ... will in fact give us 20. Let's take a look at problem 2. Problem 2, you might see, looks exactly like this right here. We have e to the ln of x equals, it should equal x. Oh, that means x needs to be 4. That's the quick way to do this problem. The answer is 4. The longer way to do this problem is do what we did in the first problem. We have e to the something, and that variable is up in the exponent. And so what I'm going to do is actually take the natural log of both sides. This looks a little bit weird because we have the natural log of e to the natural log of x. So we'll take the natural log of both sides. Again, answer is 4, and we got that from this quickly. But this is to show, if you did not see that, how we can get this in another way by taking the natural log of both sides. When we do this, we can use that power property that says we can bring our exponent out in front. So we'll have the natural log of x times the natural log of e equals the natural log of 4. Well, the natural log of e is just 1, so we have the natural log of x equals the natural log of 4. And then as we can see from both sides, the symmetry on both sides of this equal sign, x has to be 4, because the natural log of 4 equals the natural log of 4. So we get that x equals 4. Problem number 3 is semi-similar here. We just have to get the term with x in it by itself. So the first thing that we're going to do is subtract 9 from both sides. And we will get this. Then if we divide both sides by -2, we'll have e to the x equals 1. Well, if we recall here, e is just a number, 2.718, and anything to the 0 power outputs as a 1. If you did not remember that, you could take the natural log of both sides. And when we take the natural log of both sides, we do know that the natural log of 1 is 0. We can bring that x out front using the power property. And then the natural log of e is just 1, and so we'll have that x equals 0 either way. Now this did, again, require us to know that the natural log of e is 1. We've been using that idea multiple times. It did also require us to know that the natural log of 1 is 0, and your calculator can also tell you that. We could have gotten the answer just from this point up here, knowing the properties of exponents. In problem number 4, we have the natural log of the square root of x plus 2. What I'm actually going to do is rewrite this as the natural log of x plus 2, and that is raised to the 1/2. I'm doing this so we can use that power property of logs and bring the 1/2 out in front. From this point, what I actually want to do is multiply both sides by 2 to get rid of that 1/2. So of the natural log of x plus 2 equals 2 when we multiply both sides by 2. Then at this point, I'm actually going to take e to the both sides. I'm saying that kind of weird, but what we're going to end up having is e to the natural log of x plus 2 equals e squared. So we can rate both sides become the exponents and the base is e here. Now, the reason I did this is because it looks like this property here. E to the ln of whatever equals that whatever. So in this case, we have e to the ln of x plus 2. This left-hand side really just equals x plus 2 from that property. So we have x plus 2 equals e squared. And then when we subtract 2 from both sides, we'll get e squared minus 2. And that gives us approximately 5.39. Now, was there another way to solve this problem? Yes, and I always like pointing out multiple ways to look at things. Let's say you did not see that, I don't know how to say this, but take e to the both sides, whatever we did there. Let's say we were just at this point and we were unsure of what to do. We were at the natural log of x plus 2 equals 2. We know that this is logarithmic form. We understand that the base is e even though we don't see it because the base of any natural log is e. That's what makes it a natural log. We can rewrite this and say e to the exponent, because after all, a log always equals an exponent, e to the second equals x plus 2. If you remember from pre-calculus or algebra 2, whenever you learned log form to exponential form, we just went from log form to exponential form. That got us to the same point here, and that allows us once again to solve for x. And we'll still get e squared minus 2 either way, which is approximately 5.39. So there you have it. We solved 4 kind of complex looking problems involving the natural log and e. This is the graph of e to the x. This is f of x equals e to the x. We can clearly see here that it is definitely an exponential function. If we zoom out pretty far, we see that as x approaches negative infinity, here our left end behavior is 0. That is because whatever negative numbers we take e raised to, we end up just getting 1 over e to that positive number, getting closer and closer to 0. We can never output a negative value with an exponential function. That's why our range is all positive numbers. Next, if we were to look to the right and take a look at our right end behavior, we can clearly see that we approach positive infinity. It definitely shoots up very quickly here, and as x approaches infinity, so does y. A few points that we can see are that when we plug in 0, we definitely get 1 because e to the 0 is 1, and when we plug in 1, e to the 1 is just e, and so our output here is e, about 2.718. So we can clearly see we have the point 0, 1, and we also have the coordinate point 1, 2.718, so 1, e. So the graph of e to the x is just like any other exponential function where the base is a positive number greater than 1. All right, some official properties of our function f of x equals e to the x is that the domain is all reals. We could plug in any number we want. We definitely did not see any issues in our domain. However, we do see that the range is only positive numbers. We see that our function e to the x is continuous, it's always increasing, and it is 1-to-1 on the entire domain, so for all reals, meaning that its inverse, the natural log of x, is also a function. The graph of e to the x is concave up, meaning that its second derivative is always positive. And then this is something we talked about as well, the end behavior. As x goes to negative infinity, our output approaches 0. And then as x approaches positive infinity, our right end behavior, our function goes and approaches infinity. All right, now getting into the calculus of e to the x. We are going to first explore the derivative, do some examples with applying the derivative, and then get into the integral. The derivative of e to the x is very simple. It's its own derivative. That's why this number e, this weird, irrational number between 2 and 3, that's why it's so important. Well, one of the reasons anyway, and probably the coolest reason in my opinion in calculus is that it's its own derivative. Pretty sweet. But what if we have something that is not just e to the x and rather e to the maybe, 3x or something like that? Well, if we take the derivative of e to the u, we end up getting e to the u still, but then we need to use the chain rule and multiply by the derivative of u. Another way that I learned this, actually back in high school that I enjoyed, is if we're taking the derivative of e to the u, and this is just another way to write it, it's u prime times e to the u. That's simply just a different way of writing this one right here. All right, let's find each derivative. For number 1, we want to take the derivative of e to the 2x squared minus 1. So we are going to literally write out itself, e to the u. Here u is 2x squared minus 1. So we'll have e to the 2x squared minus 1. And then we need to multiply by the derivative of u prime or du dx, however you want to look at it. Well, the derivative of 2x squared minus 1 is going to be 4x. Now, usually we write e to the whatever last in an expression, so we can rewrite this in a cleaner way as 4x e to the 2x squared minus 1. In our next example, we want to take the derivative of e to the negative 3 over x. So what I'm actually going to do is just simply rewrite this as e to the negative 3x to the negative 1. Then it's a little bit more apparent on how we're going to be using the power rule here, just like we did in the first example. So we are going to take e to the u. Our u is negative 3x to the negative 1. So we'll have e, and I'll just write it the way that it was initially written. Then we want to multiply by the derivative of negative 3x to the negative 1. And so using the power rule, we'll bring the negative 1 out front. So we'll get 3, and then we subtract 1, so 3x to the negative 2. Writing this in a nicer looking way using positive exponents, we will get 3 over x squared, and then that e to the negative 3 over x is also in the numerator, so we can write it as a fraction just like that. Now let's apply using the derivative of e to the x. So we want to find the relative extrema of the function f of x equals x e to the x. Recall, finding the relative extrema is simply one of the few applications, or one of the many applications of finding a derivative. So our first step is we want to find the derivative f prime. Well, in this case, we can see that our function is clearly a product where both factors in that product involve the variable x. And so we'll use the product rule. So we will take the first, which is x, times the derivative of the second, which is e to the x. Pretty cool. Plus the second, e to the x, times the derivative of the first. The derivative of x is just 1. So we'll multiply by just 1. All right, so clearly I don't even need to write that times 1. We have our first derivative here, f prime, using the product rule. Now, if we were just asked to find the derivative, we'd be done. But in order to find the relative extrema, our second step is to find those critical points. Now remember, to find critical points, we need to find where our first derivative is equal to 0 and or where it is undefined. Now in this case, our first derivative is always defined because there's no x values under a square root or in the denominator. We don't even have a denominator. So we are simply just going to set our first derivative equal to 0. Now, how do you solve for something like this? Well, the answer to that is to factor. We are going to take out the greatest common factor, which is e to the x, and we are left with x plus 1. Then we'll set each one of those factors equal to 0. Our first factor is e to the x, and our second factor is x plus 1. One of these is clearly easier to solve. The second one, we'll get x equals negative 1. Now in this case, e to the x equals 0. If you think back to our graph of e to the x, which here you don't even have to think back, it's right here, we saw that our function e to the x never hit 0. It was always just above the x-axis, and the output never quite was 0. No matter how negative we inputted those x values, we never got an output of 0. Therefore, there is no solution to e to the x equals 0. No matter what we plug in for x, we always get a positive number. If you plug in negative numbers, you get a positive output. If you plug in 0, you get an output of 1. If you plug in a positive number, you get positive output. So this has no solution. E to the x can never be 0. In fact, any rational number to the x can never output 0. So our only critical point is x equals negative 1. Now we are not done yet. We have to find out whether or not that critical point x equals negative 1 provides a relative minimum point, a relative maximum point, or neither. We can do this using the first or second derivative test. I'm going to simply use the first derivative test because I just don't feel like finding the second derivative. So let's use the first derivative test. We know that our domain is all reals. We can plug in any x value we want, and we really just want to test this one, negative 1. And so we know that when we do test it on our f prime, we get out a 0. Now we want to plug in a number less than negative 1. We'll plug in, let's say, negative 2. I'm actually going to plug it in right here. So this is the alternate way of writing our f prime. When we factored it, it was written as e to the x times x plus 1 once factored. And I think that's easier to plug in to the factored form rather than this original form here up in green of f prime. So if we plug in negative 2, we know that e to the x is always positive, so this part doesn't matter what we plug in, always positive. But if we plug in negative 2 here, we get a negative number. So a positive times a negative is a negative output. Then we can plug in a number to the right of negative 1. I'll plug in 0. e to the 0 is positive, it's actually 1, and then 0 plus 1 is positive. So we get a positive output over here. That means our function was decreasing and then increasing because our first derivative went from negative to positive. Therefore, at x equals -1, we have a relative minimum. At -1 comma something, if we plug in -1 here, we'll get -1 times e to the -1. So that's -1 over e. So our output is -1 over e. And technically that number is approximately, just so we can check it, -0.37. Let's take a look at the graph of our function f of x to make sure that we do in fact have a minimum point, or relative minimum, at this point here. Here is the graph of the function x e to the x, our original function. And we can see that we do have a minimum point. It sort of dips down here, and it does occur at x equals -1. And then the output, or the y value there, is -1 over e, or -0.37. So we have taken what we've learned about the derivative of the e to the x function. We use the product rule to find f prime, found the critical points, or point, used the first derivative test to find whether or not that critical point was a relative extrema, and concluded, because our f prime went from negative to positive, that it in fact provided a relative minimum. We had the x value of -1. In order to find the y value, we plugged the x value back into the original function. We then checked the graph of the original function to make sure that we did in fact have a minimum point here. Let's again apply the derivative and take a look at this statistics example. We have what's called the standard normal probability density function. It is this function here, which looks kind of nuts. We do want to show that this function has points of inflection when x is plus or minus 1. Recall that points of inflection are when the second derivative equals 0 and changes sign. It is when the graph of the function goes from concave up to concave down, or concave down to concave up, meaning the sign of the second derivative changes at that point. So we want to get to the second derivative first. That's our first goal. Well, the first thing we need to do is get the first derivative. We can see that 1 over the square root of 2 pi, while it looks weird, it's just a constant. Pi is a constant, taking the square root of 2 pi is a constant, whatever. This is just the coefficient out in front. So it's going to stay as part of our first derivative. Then all we have is e to the u. Recall that all we need to do is, in order to take the derivative of e to the u, is literally write e to the u times the derivative of u. So the derivative of -x squared over 2. Now, just so we're aware, I can just rewrite this original function as e to the -1/2 x squared, if that's helpful. All right, now we're going to take the first derivative, so we'll have e to the -1/2 x squared. Then we need to multiply by the derivative of u up here, the derivative of the exponent. So the derivative of -1/2 x squared is going to be -x, using the power rule. We can write this a little bit cleaner and keep this coefficient out front, but we can actually move this negative just to the coefficient out front. So our coefficient is -1 over the square root of 2 pi, and then we have x e to the -1/2 x squared. So that's just the cleaned up version of our first derivative. All right, that wasn't too bad. Next, we want to find the second derivative. After all, the points of inflection come from analyzing the second derivative. Well, we again have this coefficient out in front. Let's just let it be. Now, we have something a little more complicated. We have x times e to the -1/2 x squared. This is a product. We need to use the product rule. Now, in the previous example, the product rule was just from x times e to the x. It was a little bit simpler. In this case, our e to the x function is more complex, so I'm actually going to write off to the side the u, v, u prime, and v prime of the product rule. So we'll say our u is just x, it's the first factor of our product, and then v is e to the -1/2 x squared. Then u prime is simple, it's just 1. And v prime We actually already found the derivative of this. It is negative x e to the negative 1/2 x squared. Recall we already found this derivative up here when we took the derivative of this term. So now we can successfully use the product rule. I'll put it in big brackets here since this coefficient is out front of all of it. We'll have u times v prime, so we'll have x times negative x. So that starts off as negative x squared e to the negative 1/2 x squared. Then plus vu prime. So u prime is just 1, so it's really just plus v. So plus e to the negative 1/2 x squared. All right, we have done the product rule. Now recall, to find points of inflection, we do have to set the second derivative equal to 0. Well, in order to do that, we do need to clean this up just a bit. In fact, inside here, I see that there's actually a greatest common factor, and that greatest common factor right here inside is this e to the negative 1/2 x squared. So we can pull that out in front here with this coefficient. So we'll have e to the negative 1/2 x squared. And then inside, what's left of this term is negative x squared. And what's left of this term here is 1. That's a little bit awkwardly written inside, so I'm actually going to change what's inside here to 1 minus x squared. We can do that just so it's written in a nicer way. All right, we wanted to set our second derivative to 0, so let's do it. We have two factors here. Our first factor is this greatest common factor out in front, and our second factor is 1 minus x squared. So we're going to set both of them equal to 0. We can see over here that although this looks complicated, we could simply get rid of this negative 1 over the square root of 2 pi, again, just a coefficient, by just dividing both sides by it. And 0 divided by any coefficient or any just regular number is just 0. So essentially, this term can just go away, that part of it. Then the e to the negative 1/2 x squared. Well, we want to think about this. No matter what we can plug in for x, it doesn't matter because we have e to that value, and we've already established that e to anything never outputs 0. There is no solution right over here. In our second equation, setting equal to 0, we will end up adding x squared to both sides and then taking the square root. When we do that, we'll have x equals plus or minus 1. Now, what we have just shown is that the second derivative equals 0 at plus or minus 1, two x values. These are potential points of inflection. In order to prove that they are actually points of inflection, we do have to test and show that the second derivative changes sign at both of them. So let's do that. So we can simply rewrite our second derivative in the factored form, which is negative 1 over the square root of 2 pi e to the negative 1/2 x squared times the quantity 1 minus x squared. That's our second derivative factored, and we want to just show that the sign of the second derivative changes at both of these potential points of inflection. All right, we know that when we plug in negative 1 or 1, our second derivative is in fact 0. Let's plug in a point to the left of negative 1. Let's plug in negative 2 into our second derivative. Again, we know that this right here, this term right here, e to the whatever with x, is positive. But then this out here is a negative. So we know that this front part here of our second derivative is always negative. Let's plug into here. We'll have 1 minus, and then when we square negative 2, we get 4. So 1 minus 4 is negative. So we'll have a negative times a negative over here is positive with our second derivative, meaning our graph is concave up from negative infinity to negative 1. Then in between negative 1 and 1, we can plug in the number 0. Again, this out front here, always negative. If we plug in 0 here, 1 minus 0 is 1. That's positive. So a negative times a positive is a negative. Go ahead and try the last one and see what you get. We will end up getting a positive over there. Now, this shows that our sign of our second derivative does in fact change at negative 1 and 1, meaning that our graph has gone from concave up to concave down at x equals negative 1, and from concave down to concave up at x equals positive 1. that means that the original graph f of x has points of inflection at those two x values. We can actually look at the graph of our function to prove this as well. Here is the graph of that original function. It is very hard to tell where the points of inflection are. However, we can clearly see that this graph kind of goes from concave down to concave up, like it'll start to hold water when x is -1, and then again it changes from this concave down where it would hold water to concave up where it would spill water at +1. It's hard to see, and that's why we needed to use the calculus to definitely check it out, but this graph does in fact have points of inflection at x equals -1 and x equals +1. Here's our last example with applying the derivative of e to the x. We have the number y of shares traded in millions on the New York Stock Exchange from the year I was born, through 2002 can be modeled by this function right here, where t represents the year with t equals 0 corresponding to 1990, so our original year. At what rate was the number of shares traded changing in 1998? So we want to know what was the rate of change at one specific point, one specific year, when t was 8. In order to find the rate of change of these shares traded, we need to find the derivative. So we have our function y, we need to find y prime. In this case, y prime is actually pretty simple to find. It's pretty much a straight up e to the x, or e to the t rather, problem. So we're going to keep that 36,663 coefficient, and then e to the 0.1902t. Then we simply need to multiply by the derivative of the exponent up here, which is just this coefficient of t. So it's times 0.1902. Now in this case, you don't really need to clean it up too much because the question is simply asking us what was the rate of change in 1998. So basically, what is the value of the derivative when t is 8? So we're going to use our calculators to plug in 8 for t. So I'll have y prime, and we can, I guess, write it of 8. It's kind of weird notation, but that's okay. So we'll have e to the 0.1902 times 8, and then times 0.1902. We end up getting an output of 31,934.56. Then, since this is an applied problem, we do want to have some units to it. So since it's a rate of change, it is something per amount of time. In this case, it's during a year, so it's something per year. The number of shares are being traded, so it's number of shares per year. So in 1998, the shares are being traded at a rate of 31,934.56 shares per year. Next, we're going to move on to the integration rules for e to the x. Well, just like its derivative, the integral of e to the x dx is, e to the x plus c. Then, of course, if we are integrating something a little more complex, such as e to the u du, it is still e to the u plus c. However, we do need to take into account that a lot of times we'll have a more complex exponent of e, and then we will need to use a u substitution. Let's take a look at these first two examples. We want to find each indefinite integral. Well, in number 1, we have the integral of e to the 3x plus 2 dx. While here you don't technically need to use a u substitution, I still am going to use one. I think it's probably the simplest way to do it. So I'm going to let u equal our exponent, 3x plus 2, and then therefore du would just be 3 dx. Well, we don't have a 3, but we do have a dx, so we'll have 1/3 du equals dx. Then we can simply replace everything inside that integral in terms of u instead of x. So we will have the integral of e to the u, and then dx gets replaced with 1/3 du. That 1/3 can go out front. So I'll have 1/3 the integral of e to the u du. We can clearly see that the integral of e to the u du is e to the u plus c, we just will end up having a 1/3 out in front. So we'll have 1/3 e to the u plus c. And then we'll back substitute to get everything in terms of our original variable, which is x. So we'll have 1/3 e to the 3x plus 2 plus c. Now, to check this, you could easily take the derivative. We can clearly see that the derivative of this would in fact be itself, but then times 3. That times 3 and the 1/3 would cancel out. We would be left with just e to the 3x plus 2. Let's take a look at number 2. It's a little more complicated looking, but it's the same idea. We have the integral of 5x e to the negative x squared. We can see that this will also be a u substitution where we let u equal the exponent of our e. And that's because if we let u be negative x squared, du would simply be x. Now, granted, it would be negative 2x, but we have that part right here. We have the important part of it right there. So we'll let u equal negative x squared, and therefore du will be negative 2x dx. Well, we don't have a negative 2x dx, we have a 5x dx, and so what I'm going to just do is solve for x dx, so we'll have negative 1/2 du equals x dx. Then at this point, we can replace everything inside the integral in terms of u instead. So that 5 is just going to stay. This e to the negative x squared is e to the u. And then the x dx gets replaced with negative 1/2 du. The negative 1/2 can come out front, and the du can stay there. We can actually rewrite this and bring the 5 out front, so it'll become negative 5/2 the integral of e to the u plus, just e to the u du. I'm getting ahead of myself. Then, at this point, we can integrate. Well, the integral of e to the u du is going to be e to the u plus c. So we'll have negative 5/2 e to the u plus c. Then we'll back substitute with what u equals and go back to our original variable x. So we'll have e to the negative x squared plus c. Here we have 2 more examples with indefinite integrals involving e to the u. In our first one, we have the integral of e to the x to the negative 1 over x squared. Now, this can be rewritten in a multitude of ways, but what I'm going to do is actually rewrite this as x to the negative second, e to the x to the negative 1 dx. The reason I'm doing it that way is so we can clearly see that both of these x's are raised to a negative exponent, and one is definitely a derivative of the other. So at this point, we can see that we want to again make u equal to the exponent of e, because its derivative is built in. The derivative of u equals x to the negative 1, so the derivative of x to the negative 1 is negative 1 x to the negative 2 dx. So we can clearly see that it's built in right here. We do have to get rid of that negative 1 though, because it's not a part of the integrand. So negative du, or negative 1 du, equals x to the negative 2 dx when we divide both sides by negative 1. Then we can go ahead and rewrite our integral solely in terms of u. So we will have the negative 1 can go out front. We will have e to the u, and this is our du right here. So we will simply have e to the u du. Integrating this gives us negative 1 e to the u plus c, and with back substitution to get back in terms of x, we'll have negative 1 e, and then instead of writing x to the negative 1, I am just going to write 1 over x since it's how it was presented in the beginning, and then plus c. In the next example, we have the integral of sine x e to the cosine x. Once again, we can see that something and basically its derivative are in there. So if we let u equal cosine x, du is the derivative of cosine, which is negative sine x dx. Once again, we had a u and a du basically built into the integrand. We do have to deal with that negative though, and we can do that by dividing both sides by -1. So we'll have -1 du equals what we have in there, which is sine x dx. So now we can rewrite our integral. That -1 can come out front, and our e to the cosine x gets replaced with e to the u. The sine x dx is -1 du. We already have the -1 taken care of, so it's just du. Integrating this gives us -1 e to the u plus c, and then back substitution gives us -1 e to the cosine of x plus c. Our last three examples are having us evaluate definite integrals instead. So once again, this is a definite integral because there are limits of integration here with numerical values. Now in part A, I'm going to do something that hopefully doesn't make you too angry. But in part A, I'm actually not going to do a u substitution here. I'm simply going to evaluate this in my head. Well, we know that the integral of e to the x is just e to the x. Yes, a plus c, but in this case we won't have plus c. So e to the negative x is simply negative e to the negative x. And that's because if you quick took the derivative of this, you would get back to here. Those negatives would end up canceling out, the -1 and this -1 here. And so when we are evaluating this from 0 to 1, we're first going to be plugging in 1. So we'll have -e to the -1. Then we're subtracting and going to plug in 0. So we'll have -e, and the -0 is not a thing, so just e to the 0. So this is really negative e to the -1 plus e to the 0 is just 1. Writing this in a nicer way, we'll have 1 minus 1 over e. In part B, we again have a definite integral from 0 to 1, but in this case it's a little bit more complex, so we will in fact do a u substitution. Think about what you want to let u equal. Well, normally when there's fractions, we want to let the u be the denominator. Let's make sure that that would work. If we let u be the entire denominator, then du would simply be, hey, we have it there, e to the x dx. Awesome. So this is really the integral from u of 0 to u of 1, since we're not going to change those values. These are x values. We are not going to change them into u values, so we can just write them as u of 0 and u of 1 instead. So we'll have 1 over u, that's this part, and then e to the x dx is our du. All right, so integrating 1 over u is the natural log of the absolute value of u. Then, at this point, we want to back substitute. So when we do that, we'll have the natural log of the absolute value of 1 plus e to the x. And we don't need an absolute value anymore because 1 plus e to the x is always positive. Then we want to evaluate this. We're back in terms of x now, so we can just write it as 0 and 1. So from here, I want to first plug in 1. So we'll have the natural log of 1 plus e to the 1, which is just e, then minus the natural log of 1 plus e to the 0. E to the 0 is 1, so we'll have a 2 in there. Using properties of logarithms, we can actually write this as 1 log. So the natural log of 1 plus e all over 2. You could get what parts A and B are as decimals if you'd like using your calculator, but from here we can just leave it. Then finally, part C, we want to evaluate another definite integral. In this case, we see we have e to the x times the cosine of e to the x. In this case, since e to the x is its own derivative, it does make sense to make u what's inside the cosine function, which is simply e to the x. So our du will be e to the x dx. Now in this case, we will have the definite integral, and now we're in terms of u, so we want to write u of -1 and u of 0, because negative 1 and 0 are x values, and we're writing things now in terms of u. All right, so cosine of e to the x can be replaced with the cosine of u, and then this e to the x dx gets replaced with du. From here, we can integrate. The integral of cosine of u is going to be sine of u. And so going back and back substituting, we'll have the sine of e to the x. And we want to evaluate that from negative 1 to 0. So from here, the first thing we're going to be plugging in is a 0. So we will have the sine of e to the 0 minus the sine of e to the negative 1. So this gives us the sine of 1 minus the sine of 1 over e. While this answer is totally acceptable, I will actually finally give the decimal approximation for one of these. This decimal approximation is 0.482. I did want to give that one, just be sure that your calculator is in fact in radian mode. These other two, it does not matter the mode that your calculator is in, and you can leave the answers just as they are or as the decimal. Congrats on making it to the end of this video. In this video, we learned a lot about e to the x, as well as how to differentiate it and integrate it. In short, e to the x is pretty cool.